Only about 33% of the surface, 0.4% of the volume, and 0.00007% of the history of the Earth is accessible by direct exploration to humanity. This is the paradox of inaccessibility. It means that by direct exploration alone, accessing the interior of our planet is comparable to attempting to deduce the intricacies of a plot of a 3-hour film by looking at a single frame with coffee spilt all over it. The geological structures of the continents are much like that found under the ocean floor. The rock at the relatively shallow depths we've drilled down to are not much like that found deep in the Earth's interior, and the past 3,500 years of recorded human history is quite frankly a drop in the ocean on the geological timescale. But through clever use of a little thing called the scientific method, we can overcome this paradox. We make observations, models to fit those observations, and predictions based on that model. Then new observations are recorded and compared to said model, after which the model is either altered or it is correct, for now. All very clever. Some very smart cookie about 300 years ago, called Isaac Newton, gifted humanity with his law of universal gravitation. This says that the gravitational force is equal to the gravitational constant times the product of the two objects' masses over the distance between them squared. Our current best estimate for the gravitational constant is about 6.673 times 10 to the minus 11 Newton meter squared per kilogram squared. All very clever. To work out the mass of the Earth, we can use two methods. First method. We equate Newton's second law and his law of universal gravitation of F equals ma is equal to g times m over r squared, in which r is the radius of the Earth. You might be thinking, Tom, I get that the big M represents the mass of the Earth, but what's the smaller mass on the Earth's surface? And to that I say, it doesn't matter, because it gets fucking yeeted from the equation when we rearrange for M. Wham, bam, thank you ma'am. The second method uses Kepler's third law, balancing the gravitational force and the centripetal acceleration, more about that another time, in which t is the time period of the orbit of a smaller mass, like this blingin' satellite, around a larger one, like this blingin' planet, and a is the semi-major axis of that orbit. We can rearrange all of that to find out the mass of the Earth. All very clever. This will give us a mass of around 5.972 times 10 to the 24 kilograms, and therefore a density of around 5,510 kilograms per meters cubed. This is considerably more than the density of rocks that we can observe at the surface, usually 2,500 to 2,900 kilograms per meters cubed, and hints that there may be a little bit more to this geophysics malarkey than we initially anticipated. Rock density is important because local changes in rock density cause small variations in local gravity. For example, you would feel a weaker gravitational force floating around in space next to a giant sponge than something much more dense, such as a big ball of lead, or someone who believes the Earth is flat. The same can be said regarding the geology directly below your feet. These small variations can be measured and recorded in 3 different ways. I don't know, maybe geophysicists are indecisive or something. In meters per second, like normal, in milligals, or, though not an SI unit, gravity units. 1 micrometer per second squared is equal to 0.1 milligals and is equal to 1 gravity unit. And them's be the basics. Easy peasy.